Hi everyone, my name is Carlos. I am a postdoc at MPE in Germany, and today I will talk about cosmic voids as cosmological laboratories. This is a project that I undertook in collaboration with Dante Paz, Ariel Sanchez, Nelson Padilla, Andrés Ruiz, and Raúl Angulo. So these are the goals of my talk. This is the message I would like to leave you with. So first, that nowadays it is possible to do high precision cosmology with cosmic voids, particularly with two void statistics, the void size function and the void galaxy correlation function. Second, that since we measure these statistics from the spatial distribution of galaxies, and given the precision achievable nowadays with modern spectroscopic surveys, it is essential a full description of the effects of spatial distortions. Here in the case of voids, we have two main sources of distortions: dynamical distortions, Kaiser effect, and geometrical distortions, the Alcock-Paczynski effect. In this talk, I will show you that, that an analysis of the mapping of voids between real space and redshift space leads to new effects that must be taken into account in order to obtain unbiased cosmological constraints. For example, we found a new class of dynamical distortions that is associated with the global void dynamics, and also we found that the intrinsic ellipsoidal nature of voids is another source of anisotropic patterns on the correlation function. So I will start my presentation with a very brief introduction. First, I will explain the two void statistics. So on the one hand, we have the void size function. Mathematically, it quantifies, it is essentially a radius distribution. So physically, it characterizes the abundance of voids in the universe. It is completely analogous to the dark matter halo mass function, so it can be modeled in a similar fashion by means of the excursion set theory combined with the spherical evolution of density perturbations. On the other hand, we have the void galaxy correlation function. Mathematically, it quantifies the probability excess of finding void galaxy pairs with respect to a homogeneous distribution of such pairs. So physically, it characterizes the density fluctuation field around voids. Due to the presence of spatial distortions, it is a common practice to represent the correlation function as a two-dimensional map with axes along the line of sight and perpendicular to the line of sight. So here the detection and quantification of the anisotropic patterns on these correlation maps is a valuable source of dynamical and cosmological information. So these are the basics for designing cosmological tests based on these two statistics. However, as I said before, given the precision achievable with modern surveys, it is essential a full description, a complete description of the effects of spatial distortions, dynamical and geometrical distortions around voids, in order to obtain unbiased cosmological constraints. Traditionally, we have focused only on the spatial distribution of galaxies, but the truth is that distortions also affect global statistical properties of voids, leading to new effects that must be taken into account properly. And very important is that this problematic affects not only the correlation function, but also the void size function. So regarding the correlation function, there are two main approaches to tackle this problematic. On the one hand, we have the reconstruction technique that tries to recover approximately the real space position of galaxies based on the Seldovich approximation before applying the void finding step. So it is an iterative process. In the end, the analysis is performed with real space voids and redshift space galaxies. And on the other hand, we have a parametric approach, which tries to absorb or encode any additional void systematics with nuisance parameters incorporated to the model for the void galaxy correlation function. So, although these two approaches work very well in constraining the cosmological parameters, here we propose an alternative approach. Why? Well, on the one hand, there are some hidden physics regarding these void systematics that these two approaches are not taking into account explicitly. So we can learn a lot about the dynamics and structure of voids from these hidden physics. And also, if we provide a physical model for them, then we will enrich a lot the cosmological tests. But of course, this approach must be understood as a complementary approach. So in this regard, we present the redshift space mapping of voids. So more specifically, we try to find a physical connection between the void identification process in real space and in redshift space using a spherical void finder. We provide a physically motivated model based on dynamical and cosmological grounds that explains how the void finder operates under this mapping. And what is very important here is that this framework that we provide is applicable to both statistics, the void size function and the void galaxy correlation function. For the second part of my talk, I will provide more details about our approach. A priori, this redshift space mapping of voids is not trivial because the case of galaxies is very different to the case of voids. On the one hand, galaxies can be considered as particles under this mapping. So they are totally conserved, only their position changes. By the contrary, voids are extensive regions. So under this mapping, some voids can disappear, whereas other artificial voids can be created. Fortunately, things are not so complicated. And this is because a fundamental result that we found, and that is voids identified above the shot noise level are conserved. So based on this fundamental result, now we can explain all the effects that act under this mapping and that are responsible for transforming the real space voids into the corresponding redshift space population. So in this slide, I will summarize these effects. And of course, this is based on our fundamental result that we can assume void number conservation. And to understand better what is happening here, you can look at this schematic figure here. Here it is represented a generic spherical real space void. So the effects that act under the redshift space mapping are the following. First, voids appear elongated along the line of sight in redshift space. And this is a consequence of the classical dynamical distortions induced by tracer dynamics. However, as we are using a spherical void finder, the net effect here is an expanded sphere in redshift space. Second, the centers of voids appear systematically shifted along the line of sight. And this is a consequence of a new type of dynamical distortions induced this time by the global void dynamics. So we can understand this effect by considering that the void moves as a whole with a net velocity. But this is not the complete story. The Alcock-Paczynski effect also affects the volume of voids. In this case, the net effect can be an expansion or a contraction. It all depends on the selected fiducial cosmology. So we provided a theoretical description for all these effects based on dynamical and cosmological considerations. But what is important here is that this formulation depends strongly on the cosmological parameters. So it must be incorporated into our current models for the cosmological statistics, the void size function and the void galaxy correlation function. And also we provided a very complete statistical analysis to prove all these effects. So for the last part of my talk, I would like to show you the impact that the redshift space effects in voids have on the cosmological statistics. So I will start with the void size function first. For this analysis, please pay attention to the left-hand panels and forget about the right-hand panels for the moment because they only show some technical stuff. In particular, look at this panel here at the bottom left. Here you can see the void abundance obtained from the Millennium Extra Large simulation in 4 different situations. Here the blue curve represents the true abundance in real space. Here in red, this is what happens if we consider dynamical distortions only. And finally, with purple and green, we also consider what happens if, with geometrical distortions, considering 2 fiducial cosmology. So the last 3 mimic possible observational measurements. And as you can see here, the deviations between the curves is very significant. So the goal here is to correct the abundance curves in order to recover the true underlying one in real space, namely the blue curve. And for that, we have to apply the framework that we provided for explaining the redshift space effects in voids, namely the Alcock-Paczynski volume, the expansion effect, and the off-centering effect. But here, in the case of the void size function, we only care about the volume of voids. We don't care about what happens to the centers. So in this case, we are free of the off-centering effect. And the correction can be performed in 2 steps. First, we correct the void radius for the Alcock-Paczynski volume, as you can see here in the middle panel. Then we correct for the expansion effect, as you can see here in the top panel. And regarding the correlation function, let me introduce first the projected correlations method that we developed. This is because in this way we can maximize the way in which we extract information from anisotropic patterns observed on correlation maps. So essentially what we do is the following. We project the correlation function towards the plane of the sky axis in a given redshift range, and we obtain the plane of the sky correlation function that is simply a 1-dimensional profile that depends only on the angular coordinate. And then we do the same perpendicularly. We project towards the line of sight axis in a given angular range, getting in this way the line of sight correlation function that again is simply a 1-dimensional profile that depends now on the redshift coordinate. Here in this figure, you can see an example of the projected correlation functions with data obtained with data from the BOSS survey. As you can see here, the line of sight projection represented in red is very sensitive to the redshift space effect in voids. And another positive thing is that we can measure the projected correlations with an excellent signal-to-noise ratio. So this is very promising regarding the new surveys. And in fact, if we correct our model for the correlation function, taking into account all the redshift space effects in voids that I introduced before, it is not enough. There is still a large residual. And lately, we found that this residual is due to the intrinsic ellipsoidal nature of voids. This is an effect that we call the ellipticity effect. So voids are better characterized as ellipsoids rather than spheres. And this is a source of an additional source of anisotropic patterns on correlation measurements. At first, we figured out the existence of this new effect by measuring density and velocity maps of void samples in real space, where we detected anisotropic patterns in real space. So I move to my conclusions now. Cosmic voids are promising cosmological proofs for testing dark energy and alternative gravity theories. Nowadays, we can do high-precision cosmology with the void size function and the void galaxy correlation function. However, it is essential a full description of the effects of geometrical and dynamical distortions around voids in order to obtain unbiased cosmological constraints. So to address this problematic, we developed a theoretical and statistical framework, the redshift space mapping of voids, that is based on cosmological and dynamical grounds. And we found very interesting new effects that were not taken into account previously. And finally, I also showed a different technique for measuring correlations that is based on the projected correlation functions that allow us to maximize the extraction of information from anisotropic patterns. And another positive thing is that the projected correlations also allow as to significantly reduce the number of mock catalogs needed to estimate covariances. So that is I finished here. So thank you very much for your attention. And here you can find my work.